See, I'm getting all the numbers.
All right. We'll get underway. First thing I want to address a couple administrative items. So as a reminder, next Thursday we will not meet here, right? We're meeting at Midland Hills Country Club in, I forget if it's in Falcon Heights or Roseville. Maybe it's in Lauderdale. Anyway.
Is it the same place as last time we were there?
Yeah. Those of you who have been there with me before. But you do have a link in the calendar invite that I sent you, right? Okay, so for directions to get there. The topic is going to be moisture mitigation in concrete slabs, which, if it has not been a problem on a project of yours, it likely will be at some point. And so what I've included, I added up in this technical review document, NRMCA CIP 28, and this is on concrete slab moisture. Make sure to read it over because we'll talk just for a few minutes on Tuesday morning, just so that when you walk in on Thursday, you're not like, why are you here? Or, this guy told me I had to be here, right? Okay, so you got a little bit of something that you're going to be aware of. But if you aren't familiar, NRMCA is the National Ready Mix Concrete Association. So they're based out of somewhere in Maryland. I forget where exactly off the top of my head. But they have a number of documents, and they're called Concrete in Practice. And I'm working with the library on seeing what our copyright sharing rights are. They've got a total of about 54 of these documents. And I've got them up at my desk. If I could share them all with you, once I figure out from the library, I gladly will. I think there's a lot of good beneficial information in there. Okay, so before we come back to class next Tuesday, make sure that you read through this document. Okay, so you're a little bit aware of what's going to be going on. Okay, so regarding the breakfast itself, I've got for you, and you should be able to see this, summary of the MCC breakfast meeting. Okay, so just looking for a short response from you. It's going to be worth, what did I say, 10 points? And I think I put, I don't know, I'm forgetting if I said 7 for the summary and 3 for business cards, or 6 for summary and 4 for business cards. I forget off the top of my head. But I want you to at least introduce yourself to 2 people that are there. Okay, so maybe they're a contractor, maybe they're an engineer. I'm less interested with defining who it is that you talk to. I just want to make sure that while we're there, we're doing a little bit of networking. You guys are growing your network for once you get out into industry. Okay. Also, you can't just talk about the food. Okay, so you got to talk about the program itself. I already know how good the bacon is. I don't need to hear it from you. Okay. So, questions on that? And if you haven't already seen an email from Margaret Mills at MCC confirming your attendance, you should see that in the next week or so. Okay, the next item, and this is right up above the summary. So this will be our next lab. I talked about it a little bit. Gosh, maybe it was 3 class meetings ago. And full disclosure, this is the first time running this lab in a class for me, okay? So we're going to chunk along a little bit, but I think that I've got it mostly thought out and fleshed out what we want to do, okay? So I've got a document for you here. So the big thing is, I think you've all been upstairs and used the test frames up on the black level, right? Doing pull tests, okay? So we'll be back up there for that using the test frame. As far as other items needed, that's really going to be defined by you and what material you're selecting. Okay, so I don't want to provide a lot of restrictions on what it is that you're choosing. And so again, what I said is, I had a pallet of stuff not too long ago, so I cut up the plastic banding strips. And I'm just gonna take a commercially available epoxy and epoxy these things together. All right, and so, and I'll take that up and I'll test mine with you. Okay, and I'll use that to, we'll talk about the assignment here in just a little bit, writing a lab report. I'll use these test results to write an example lab report to provide you guidance on what it is that I'm looking for feedback, okay? So, the main guidelines in your selection of the material is something that becomes part of the waste stream on a construction project, okay? Maybe you want to make your own fiberboard, okay? And so you're going to grind up a bunch of plywood into sawdust and glue it together, making a composite. By all means, go ahead, okay? Maybe you have somebody shipped a bunch of stuff with kind of a leather cloth binder, and you want to check and see, could we use that material? Could we use it for something? Okay, so not terribly interested in providing you any constraints on what it is that you're selecting. Okay, it just has to be something that at some point would make it into the waste stream on a construction project. I'm also not advocating that you go around to construction projects and dig through their dumpster. That's not what I'm saying also. Okay, so it's not that it has to be, I mean, if you're throwing stuff away at home and you're thinking about it, like, hey, I wonder how this thing could work. I wonder if this thing's going to use. Now, I don't know if we want to go so far as to say, well, I cut up a cucumber this week for dinner, so I have a bunch of cucumber shavings. I don't know that we're taking it that far. Okay, so it's not necessarily part of your lunchbox that you're throwing away. Okay? Does that make sense from a material standpoint? What expectations are? Okay. And so next Tuesday, we'll give you time in lab where if you need to cut stuff up, if you need to make any changes to it and use the equipment here, you'll have that time, okay? So, but the big thing that I want you to focus on is how would you actually use this thing on a construction project? And I'm not saying that you have to come up with, I've completely mocked up a 10-story structural frame that I'm going to use this product for. Just think about it. Do you think that you could use it as a structural component? Do you think that it could be used as a finish material? Do you think that it could be used as some sort of repair material? Okay, so think of it more as a generalized state at this point. Okay? We should have 2 specimens when we get ready to test, just so that we can get an average of test data to see what's going on with it. Okay, so the idea behind it is, since we'll be fabricating them next Tuesday, then on Thursday we're at MCC, we'll test them the following Tuesday. Okay? So, on the day of testing, so we'll test in displacement control rather than load control. Okay, which when we were up there in the past, we did load control testing. We did displacement control testing. When we've tested concrete cylinders, we're doing load control. Okay? And then after spring break, when we're working with concrete, we do flexural beam testing. Then we'll get back into load control testing again. So you get a chance to see both of those again. Take pictures of your test specimens prior to testing. Take pictures of them following testing. Okay? And then just determine the stress resisted by your material. Okay? And it's a direct stress test, so it's just the maximum load divided by that cross-sectional area. Okay? And then just provide summary lab report detailing all of this stuff, submitted as a PDF to Canvas. Okay? Seem reasonable? Okay. So we'll tackle that on Tuesday. Is there anything else that I needed to say? I got you the CIP document. We talked about MCC. Oh, it's spring break pretty soon, isn't it?
Is it?
2 weeks from today will be our last meeting prior to spring break. So, we'll do the midterm at that point.
2 weeks from today.
2 weeks from today. So, you'll see down here in chapter 9, oh, you know what, I didn't even think about it. I gotta go in and change. There's gonna be method of sections on there, or method of joints. I gotta pull that off because we didn't do it. We did forces, We did force resolution, we did axial load, we did shear, and we did bending. Okay, so those are gonna be the topics that you're gonna be assessed on for the midterm. Okay? Yeah.
Is it like open notes at all, or?
Oh yeah, yeah, it's like all my other classes. Yeah, I'm not interested in you memorizing things. We're not interested in seeing how well can you draw a shear diagram from memory. No, you can use notes and assignments and things like that. That's how we work in the real world. So, it's a good question. Okay, so I'll adjust that. Hey, let's hold it down. Okay. Other questions initially on the midterm? We'll take a little bit of time on Tuesday to talk through it too. I'll doctor it up and get the method of sections and method of joints off there so that you don't have increased heart rate while you're studying. Okay. Okay. If anything else comes up, let me know. I'm starting to get classes back under control, thankfully, in the last week. So, questions on homework?
Can you go over D?
Sure.
It's,
On the last one, the current one.
Okay.
so we got a beam, and then there's a load on top of it that's 200 pounds per foot.
Okay.
And then after 10 feet from the left, there's so it's 12 kilos, I would assume. So 10 feet from the left, it's 12K going down.
Okay. And so that one, so we had a question on that.
Oh,
Improperly labeled, that should be 12 kips.
kips.
Oh, God.
Yeah.
No wonder that was
Okay.
so hard.
Yeah.
See, I converted kilos to
I
pounds.
can-
That's fine. I mean, if you did that, and as long as you include your notation
Yeah.
for why you did it, what the change was, I'm fine with giving you full credit. I forgot to look at those, and I forgot that notation was in there.
It's a good switch.
Do you still
I
wanna
guess
look
you
at
don't
it?
really have to go over it now unless someone else wants to, but
It's up to you.
I think we're good.
We're good? Okay.
No, I did it in those like kilonewtons and years. That's the ones that
Sure.
I was doing.
Yeah. Yeah, I mean, they want to sell the books internationally as well as domestically, right? I mean, they're probably printed in China anyway, but.
It was cool. It's a good way to actually, I don't know, put your
Yeah.
skills to the test.
Yep.
You know.
Yep. Other questions?
The V equals 0, that's where it breaks the line. And the V max,
What do you mean breaks the
like when
line?
it dips, but like where it would shear.
Well, it's not necessarily that it's going to shear there, right?
But that's, yeah, where.
Because remember that this diagram is the diagram of shear, okay? And when it crosses the line,
Yep,
so you're talking this point,
that's.
Right?
0, yeah,
that's where shear equals 0.
okay.
Okay, so we'll actually never fail in, well, it's incredibly unlikely we'll fail in shear there.
And
I don't like saying things like never or always.
The V max, I think
Yep.
for the most part I did okay with. I think 1 or 2 I mixed up. The V max it's just the highest number, like at all, or
The highest absolute value.
Okay.
Right?
So if a beam, like say R1 is pushing up 10,000, then that would be the highest. If that were the highest number, that would be it.
Yeah,
Okay.
yep. And again, remember that the concept behind it is we denote it this way so that we're aware of how are those forces being exerted on the beam, okay? The beam has no awareness of what that means, right? It's like trying to talk, if you got a dog or a cat, trying to explain time, right, to an animal. They don't, not only do they have no idea what you're talking about, they're not interested, right? The beam doesn't know, and the beam doesn't care if the greatest load is coming from beneath, from on top. I mean, we've oversimplified these problems and we're only thinking about them two-dimensionally, right? We could also potentially shear in and out of the board as well, right? And doesn't matter to the beam. We just have to determine what that maximum is, okay? Great question. Is there a problem that you wanted to walk through to look at it, or you just wanted to talk through it conceptually?
I just talked to it.
Got it.
I think I did okay. I just rolled the wrong numbers for the VMAX a couple times.
Got it.
Yeah, everything else is good though.
So you're writing, so you maybe had like,
Like this one in particular, my R1 was 9,000.
This?
Yeah.
and you're picking the 6,000?
It was actually flipped. Like it's
Okay.
pushing up 9,000, then like one of the ones below would be 6,000. I was like, oh, I think this is the VMAX.
Gotcha.
So it's the highest number other than the R1 and the R2.
Gotcha,
Yeah.
gotcha. And the big thing to remember when we're talking about this is at our reactions, our shear is going to be equal to 0, right? Because we have it restrained at that point. And so you're actually not going to fail there. But where you're going to pick up that maximum shear is right when you get off that reaction point. Okay, that's when that element is going to start feeling that stress and start having to resist that. Okay? Yeah.
Do you have the mic on? Just wanted to the video.
I do not have the mic on. Thank you.
Yeah.
So that's a good 5 to 6 minutes of worthless video for everybody.
Yeah.
Yeah,
One of the videos cut out. So.
I think I didn't think
Yeah.
that the R1 and the R2 counted. That was the
Sure.
issue that I was having.
Sure. Oh, now I have to remember which one goes with footage. Oh, okay, there we go. Well, now there will be audio. Okay, so we won't summarize everything. Check Canvas, right, for notes, those who aren't here. I guess the major items that we talked about, what did we talk about? Maximum shear, right, is going to be the maximum absolute value. The material doesn't care where the shear is acting from. Here you have no shear, but that's good for us for awareness of our bending diagram because where our shear equals 0 is where we're going to have our maximum bending, okay? So, Christian, thank you for pointing me out that there's nothing going on with the mic. So, okay, do you want to look at another bending example then to help with the homework?
Yeah.
Okay. And we should maybe look at, Aaron, you made a good point. Are any of the problems, do we have a beam in any of our problems that aren't just simply supported like this? Do we have anything where we have a cantilever at all on your homework? Do you have the homework handy there, Hunter?
Not this one.
Done.
I'm looking for the page. 3.3. I've got the book here too, so.
It's the same questions as 3.2. So
Oh yeah, that's right. Yeah, we just go back and do the same problems, right?
it shouldn't be too tricky, right?
Yeah, so yeah, no cantilevers. Okay, so let's consider the case, and this green marker isn't going to show up too well on the video, so let's,
Okay.
Especially after like going for something.
and let's do a couple point loads. Okay, so scale got a little wonky there in the middle, but we've got an 18-foot span. Okay, 2 feet from R1, we've got 600 pounds. 5 feet from R1, we've got 1,000 pounds. And then from 9 feet to 18 feet from R1, we've got a uniformly distributed load, 500 pounds per foot. Okay? So, as a reminder, the steps that you need to undertake for this: determine equilibrium. Okay? Diagram your shear, making sure that you identify your maximum shear and the location of where your shear equals 0. And then diagram your bending and determine your maximum bending moment. Okay? Yeah.
Question about the homework. Do you, since we're doing the same problems over again, do you just want us to just do the
Yeah, that's what I was just going to say. We've already, for these problems, you've already done equilibrium, and you've already done the shear diagrams. You do not need to reproduce those for this assignment. Okay? Generate your bending diagrams off of those, off of that work. Okay? Yeah. I'm fine with you reproducing them from the work that you've done.
Oh, okay.
Okay? Unless you want to do the new assignment. So, no odd question there. There's a student that has a previous edition that is wondering about how to analyze those. Okay, so Hunter, great question on reproducing those. So the question, maybe the question wasn't heard. Since you have done for this assignment, you've done the equilibrium determination, you've done the shear diagram, only need to do the bending diagram, determine that maximum, okay? So this one, however, we haven't established equilibrium, we don't know the shear diagram, so let's walk through that. Okay, so setting up our 3 cases. We're still going to neglect friction, wind loads, snow loads, all that stuff, right? So we know that we're good in the X direction. What do we have going on in the Y direction? Lots of stuff, that's right. I want to make a real nice messy bending diagram for you. Because if you can do this one, then the homework will be easy, right?
So you got negative 600.
Negative 600. Okay. Yep.
negative 4,500.
And negative 4,500. Right, because 500 pounds per foot, it's applied over 5 feet, so 500 times 9 gives you 4,500. And then R1 and R2 have to resist all of that, okay? Otherwise we won't be able to complete the problem because the beam's going to fall down on the ground, right? It's not going to be up there on the board. So, R1 and R2 have to sum to 5,500, 6,100 pounds. Okay? Everyone agree with that? Okay. Do you want to analyze about R1 or about R2? R1? Okay. So, what's tending to cause rotation about R1? 600 is? How far away is it? It's 2 feet away. And is it giving us positive or negative rotation? Based on the notation that I have up here. It's going to be positive, right? Because we're grabbing on, 600 spinning us this way. Okay, and again, as a reminder, if you write left-handed and you prefer to do right-hand, because that's the only reason why I do left-handed, is then I can look at it and keep drawing or keep writing. You're going to get the same values. It's just what we write up here as positive will be negative on your sheet. What we write up here as negative will be positive on your sheet. Okay? So 600 pounds times 2 feet. What else?
1,000.
We have our 1,000 pound. And that's 7 feet away.
4,500.
4,500 pounds. How far away is that? 13 and a half feet, right? Everybody follow how Zach got that? So Zach took his 500 pounds per feet, multiplied it by 9 feet, dropped it at the midpoint, right? And then remembered that not only does he have to go this 4.5 feet, but he has to march all the way back to R1. Okay, so he's got the 4.5 feet, and we've got the 9 feet. Very good. What else do we have?
It's got to go from the center of here. So we know this is 9 feet. Plus we go
R2? How far away is R2?
18.
R2 is 18 feet away. Is that positive or negative? It's going to be negative, right? Good. So, if this all has to equal 0, 18 R2 pound feet has to equal, well, we got 1,200. And we've got 7,000. And if somebody can crank on that. 60,750. Okay. So that becomes 68,950.
Yeah.
We'll divide that by 18. 3,700 something. Sorry, say it again.
3,831.
So R1 is 3,831.
R2.
R2.
R2, yep. Thank you. Okay. So if R2 is 3831, how much is R1? 2269. Does that make sense physically? Hopefully it makes sense to us, right? We've got 1,600 pounds on the left side of our beam. We've got 4,500 pounds over on the right side of the beam. So R2 should be picking up a significantly larger amount of that load being placed on the beam. Okay? So we're good there. We're bigger by about half again. Okay? So let's draw our shear diagram. Come on. And we're going to march left to right. Okay? So what happens right when we step off over that reaction? What's trying to shear that beam?
600 pounds.
Our 2269, right? Our reaction is trying to shear. Okay? Then what does shear do for the next 2 feet?
Minus 600.
At 2 feet, it's going to drop, right?
Oh, yeah.
Yep. But we're going to march along, right, a straight line for 2 feet. Let's see, we got 9 there. So probably here. And then, Jacob, we're doing what?
Minus 600.
Then we're dropping 600 feet. Probably looks something like that. Okay. Then what do we do? Do you have a question? You just stretch it. Okay. Okay.
March 5 feet.
Then we're going to move along for the next 5 feet, right? And then do what?
Drop 1,000.
Then we're dropping 1,000. Now what are we going to do?
Go 2 more feet.
Go 2 more feet.
Then drop 500.
Then we're going to drop 500 pounds a foot, right? Until we get to down here where we're at 3831.
So even though that weight hits in the middle, you start drawing this drop wherever it starts.
Say that again. Sorry.
I think on the previous homework, I was thinking that because it hits at 13.5 feet, that's where I start the decline.
I see, I see.
Yeah.
So that we're only doing for our equilibrium, right? We're still, when we think about the beam under operation, right? It's going to start picking up 500 pounds per foot right there. Yep. Okay, so what is our maximum shear? 3831, right? That's the largest absolute value. That's what's going to control our beam sizing and shear. Okay? Now, how are we going to determine where shear equals 0?
We go at, what's that, 9 feet,
Yep.
and then subtract 500 from 669 until you get to 0.
So you want to say at 9 feet plus 669 pounds divided by 500 pounds per foot?
Yeah.
Okay? Yep. I like that idea. So plus 1.3. Sounds good. Everybody come along on that one? Follow what we're doing there? So we said, oh, and right, we should say from R1, right? Alternatively, we could say 7.7 from R2, same thing. Okay, good. So what do we know about our bending diagram? Where is your maximum bending moment going to occur?
7.3.
It's going to occur 10.3 feet from R1, okay? Because that's where your shear equals 0. Now, when you're diagramming this, we should get a point in each of these 4 sectors and at your maximum, okay? So we'll need 5 data points for this one. So how about the moment where x equals 1? X equals 1 foot, sorry. So again, we're going to move left to right. And we're only gonna think about, we're not grabbing onto the reaction, okay? We're gonna grab onto the beam and make a cut. And we're gonna think about everything to the left, how is it trying to rotate? Okay, so we move 1 foot away. What's trying to rotate?
2269.
Our 2269, right? And how far away is that? 1 foot away, it's the reaction, right? It's gonna be however far along we're marching on that beam, that's how far away our reaction is going to be, okay? What about 4 feet away? We have R1. What else do we have?
600.
Our 600-pound load is going to be acting, right? Because now we're grabbing on in section 2. Okay? Is it going to be positive or is it going to be negative? How's it going to try to rotate where we are? Is it rotating us this way? Is it rotating us this way?
Negative.
It's going to be negative, right? Because R1 is trying to spin us this way. Our 600-pound force is trying to spin us this way. Okay? Because that's the big thing conceptually, is to remember that don't grab on at the reaction, grab on. Here we're grabbing on 4 feet away from R1, okay? So, minus 600 pounds, and how far away is that? If we're at 4 feet,
2 feet.
it's 2 feet away.